right, this is computer graphics. Video 2. This video specifically is on translations / shifts. And so the goal here is to, of course, represent a shift or a translation by a matrix multiplication. This could be in 2 or 3 dimension. So, and again, for this to happen, it needs to be linear. So, in order to do this, the translation needs to be linear. And again, just to clarify, this translation shift could be in 2D or 3D is where we're focusing. So first thing we encounter is a problem. So look at the two-dimensional case, for example. Right? Suppose we're in 2D. So a point in 2 dimensions can be represented by a vector. So is the mapping f of xy, so translation would have to shift it, for example, by plus a and plus b. Is this mapping linear? And again, just to make sure that we see this right here, this is a translation by a in the x direction and b in the y direction. So the problem is it's not. So at the end of the previous video, we saw that a linear mapping needs to take the 0 vector to the 0 vector. And so look what happens here. If I plug in 0, 0, I get AB, which is not 0, 0. I mean, unless A and B are both 0, in which case it's not a translation at all. So not linear, no such matrix. This should make us worry. Because if it's not linear, we can't write down a matrix, and we can't do this with matrix multiplication. So this is a problem. Now, luckily it's a problem we can resolve. So in order to resolve it, what I'm going to do is I'm going to go back to 1 dimension for a second. Because in 1 dimension, we can see the problem a little more clearly and see how to resolve it, or at least I can give a resolution and we can understand what's going on. So here's the deal. In 1D, so a translation looks like this. F of x is x plus a. Simple shift. Also not linear. 0 doesn't go to 0. So this is what we'll do that's sort of sneaky, and don't worry about where this comes from. It's not really obvious. It's sort of created, but it's easy to see that it works here. So instead, here's the sneaky trick. We'll represent x by a vector in 2 dimensions. Even though it's a 1-dimensional object, we're represented by a vector in 2D. Specifically the vector x1. Then observe the following interesting fact. If I take the matrix 1a, 0, 1, and I multiply it by x1, we get x plus a1. So if we focus only on the first entry, right? If we focus just on that entry, we get a translation. And if we focus only on the top entry. We get the desired behavior. Let's say the desired translation. So before we go back to 2D, let's ask, just interestingly, like, what's actually happening? So let me clear the screen and draw a picture that'll help us see what's happening in the one-dimensional situation. And then we can go to 2 dimensions, and once 2 dimensions make sense, we can jump to 3 dimensions, and then we're good to go. So look at a specific example. Consider the matrix, say 1, 3, 0, 1. What does it do to xy in general? Well, if we multiply it, we can see this is x plus 3y and y. So what's happening here is that if we look at where the points come from and go to, this point goes to this point. The y value is fixed. The x value goes to x plus 3y. So visually, what's going on here in two-dimensional situation? So for example, when y is 0, this line, this is the line y equals 0, this is fixed. The line y equals 1. All right, so y equals 0 is fixed because it's specifically x0, according to our mapping, goes to x0. This line, x1, goes to x plus 3, 1. So that goes to the right by 3. The next line, right here, x2, this goes to x plus 6, 2. Again, we're using this mapping to find this. So this goes to the right by 6. The line down here, for example, right here at x negative 1, this goes to x minus 3, 1. So what's happening, this is something called a shear transformation. So the horizontal axis, the x-axis, stays put. The stuff, as you go further up, moves further and further to the right. This should have been a right 6. This is a left 3. The point being that right here, the place that we're focusing, the x1, these shift nicely to x plus 3, 1. So the practical upshot of this, before we go back to 2D, is by representing x by the vector x1, the matrix 1a 0 1, this does the desired translation to x plus a 1. So this is looming question now is, okay, how does this work? Can this work in 2D and 3D? The answer is yes. So what I'll do is I'll clear the screen, and then we'll go back to 2 dimensions, and we'll be very specific about how we work out what matrix we need. And then once we see that for 2 dimensions, it's really easy to see for 3 dimensions, so we don't need to work out all that detail. So I'll clear the screen, go back to 2 dimensions. So 3, we'll say back to 2D. So we'll try and follow the same idea, right? So given a point xy, what we'll do is we'll represent it by the vector xy1. Because this was what happened before. We added a 1 on, then we found a matrix that does the job. So now the question is, can we find a 3 by 3 matrix let's say called M, such that when I take M and I multiply it by xy1, I get x plus a, y plus b 1. Right, that's the goal. That way we can sort of ignore the third coordinate and use the matrix multiplication to do the translation. Right, so this would be nice. So what we'll do is we'll look at what this matrix would need to be, right? Because what we're basically asking here is to do this, this needs to be linear. So our mapping, our F, that takes xy1 to x plus a, y plus b 1 must be linear. So instead of checking that from the definition, this is what we'll do, is we'll find m of the basis vectors, like m of 1, 0, 0, m of 0, 1, 0, and m of 0, 0, 1. We'll look at what m would need to be, or rather f of those. We'll look at what m would need to be, and then we'll show that this m does the job. Right? So here's our approach. So observe the following. What would f of 1, 0, 0 need to be? Well, we want f to be linear. In other words, if it's linear, right, ideally, this is what we would need. Keeping in mind we only know, let me circle this, this is what our behavior needs to be. So what do we do with 1, 0, 0? So I'm going to rewrite 1, 0, 0 as 1, 0, 1 minus 0, 0, 1. The reason for doing that is if it's linear, I can split it up. And again, we're sort of hoping it's linear. We're saying like, well, if it's going to be linear, how would it need to work? Now, if I apply this, the first entry, I'm using what's in the blue to the left. This would have to be 1 plus a, b, and 1. This would have to be a, b, 1. And this turns out to be 1, 0, 0. So 1, 0, 0 would have to go to 1, 0, 0. F of 0, 1, 0. This is f of 0, 1, 1 minus 0, 0, 1, which is f of 0, 1, 1 minus f of 0, 0, 1. This would need to be a 1 plus b 1 minus a b 1, which is 0, 1, 0. And last but not least, f of 0, 0, 1. I don't need to split this up because I can just use the blue equation as is. This would need to be a, b, 1. So here's the deal, right? If f is linear, then the matrix for it would be m equals, I take these three vectors that we just did, put them together. So does this matrix do what f does? So let's take a look, right? So again, we want to know if the matrix multiplication does this thing right here. So all we need to do is calculate it. If it does the job, then we're good. And then we can move to 3D. Right? So let me clear the screen and do that calculation. So let's see. If I take this matrix, and I multiply it by xy1. Simple calculation shows I get x plus a, y plus b, 1. So the answer is yes. So what this means is, to translate in 2D, we represent the point xy by the vector xy1, and then multiplication by 1, 0, a, 0, 1, b, 0, 0, 1, will translate by a in the x direction and b in the y direction. So, for example, then we can look at 3D. To translate by, say, 4 in the x direction and negative 3 in the y direction, we're going to use the matrix 1, 0, 0, 0, 1, 0, 4, negative 3, 1. And for example, to translate, say, the point 7, 6, what we do is we take that matrix, we multiply it by 7, 6, 1, we put the extra 1 in there. When we do that, we get 11, we get 3, and we get 1. And so the result of this is the point 11, 3. That's badly written right there. So we've done the translation. That works. Now, before we move to 3D, let's define T of AB to be this matrix. That way we just have it handy. So last thing then, of course, is what about 3D? So in 3D we do the obvious. So without all the explanation. So to translate XYZ by, say, A in the X direction, B in the Y direction, C in the Z direction, we represent XYZ by the vector XYZ1 and multiply by, we'll call this T of ABC, which will now be a 4x4 matrix. But you can sort of see the pattern at this point, which is why we don't need to write it all out. And we simply multiply by that. So, for example, and then to end, say, so to translate 1, 4, 3 by, say, 2 in the X direction, 5 in the Y direction, and 8 in the Z direction. We just construct the matrix 1, 0, 0, 2, 0, 1, 0, 5, 0, 0, 1, 8, 0, 0, 0, 1. We multiply it by 1, 4, 3, 1. The result is 3, 9, 11, 1, which we then take out as 3, 9, 11. Now again, this might seem like an awful lot of work for a translation, but the point is that we've got it in terms of a matrix multiplication now, which will be convenient once we want to start combining it with other operations. So that's the end of translations for now. Next thing we'll do is, in the next video, is move on to rotations. First in 2 dimensions, then in 3 dimensions. So we'll call that the end.